All right, so during the last lectures, we discussed about how to use the basic kinematic equation. We derived the equation for constant acceleration motion, and then we tried to solve some questions, some problems with um, the equations that we have derived. And so all those are basically the analytical method of approach. All right. Now today we want to talk about the graphical interpretation of all the equations we have derived, the graphical interpretation. You have been familiar with a very few of them, like the velocity time graph you did in your secondary school. But then we're taking it further and we're trying to understand the graph, all right, what it really means. How do we interpret them? And how can we relate them to the equations we have derived before now? All right. Now, you need to understand that the interpretation of the differential equations that governs the rectilinear motion can be very simple if we establish the relationship among all the values we have. Like, let's say, among S, among V, A, and C, and C graphically. All right. So that's what we're about to do graphically. So what's the relationship between this S, V, A, T? That's the position, the velocity, the acceleration, and the time. Graphically, what's their representation? So the first one I want to talk about is if we have a schematic plot of the variation of S, which is the position with T, if we have the schematic plot of the variation of S with T, from the time interval, let's say from T1 to time T2 for some rectilinear motion, all right? So by constructing the tangent to the curve at any point T or at any time T, we obtain the slope, which is the velocity. So what am I trying to say? The first off, if I want to show the graphical representation between S and T, don't worry, I'm going to use question to solve it. I just want to give you all the graphs in a glance, just for you to see something. There's something I'm trying to drive at. Okay, now, if the curve gives us something like this, if the curve gives us something like this, and let's say initially this was T1, and let's say the final, I'm considering this as T2, considering that as T2. Now, if I take a tangent, to this curve at any point, let's say this is a tangent, and I take the slope of the tangent, so this is the slope of the tangent. So what's going to be this slope? What's going to be the interpretation of this slope? In mathematics, you know that if you want to get your slope, just going to write it here, mathematically, your slope under coordinate geometry, mathematically, your slope is dy dx. All right. So, which means you will just simply trace this to this here at this point and at this point. Then you trace this to this point and at this point, which simply means here is like your dy from mathematics knowledge, here is like your dx. And if that is a dy, that's a dx, this is the slope you're trying to take, this straight line, the tangent. So if I'm to represent it here, this dy is same thing as dx, because the representation of this coordinate is x, and this x here is same thing as dt. Okay, so if I want to get the slope now, from here, if I want to get the slope, so the slope is going to be dx and dt. And so if the slope is ds dt, that gives us what? ds dt, same thing as what? Gives us the velocity. All right? The slope is same thing as the velocity, and velocity is same thing as what? S dot. The same thing as S dot. So we can get our velocity from the position time graph. All right? The velocity is the velocity. Let me take off the slope now. Let me write it in ds and dt, ds dt. So what we are trying to get here is that we can determine the velocity, all right, at all the points on the curve, all right. We can determine the velocity at all the points on the curve, which means that the slope we obtain in this diagram of st is the velocity. The slope we obtain in this diagram, in this st, is the velocity. So we can get velocity from position time graph by taking tangent to the curve and getting the slope to the curve. So that is the first thing you need to understand there. Now, what if at every point on this st curve, if I plot my velocity, so don't worry, we're going to solve questions with that. If I plot my velocity at every point on this curve, if I plot my if I want to plot my velocity time graph, that is all the velocity I get at every point in this st curve, if I want to plot it against time, so let's say we have velocity time graph now. So that means we have velocity here and we have time. So if I want to plot the velocity time graph, and let's say this is my curve, this is my curve. Now, if I take a tangent, so let's say at point C1, I'm decided to take my initial state here, C1, I'm taking my final state here as T2. So if I take a tangent to this curve, if I take a tangent to this curve, and I want to get the slope. So what's going to be the slope? Remember, dy ds. So if I take this upper and lower, and I take this here, and I take this here. So you know that I take an elemental stripe here, an elemental stripe here. Okay, so you know that if I take the slope of velocity time graph, what am I going to get? It's going to be acceleration, right? The slope here is this vertical. Okay, let me just write it there. This vertical is going to be dv, and this here horizontal is going to be dt. So which means the slope of the velocity time graph is going to give me what? Acceleration. So acceleration is dv dt. The acceleration is dv dt. So on the velocity time curve, at any instance, it gives us the acceleration at that particular instant. All right. And if that be the case, of course, you know, this is same thing as v dot. This is same thing as v dot. Okay, so if I get the acceleration, of course, this elemental stripe is dt. This elemental stripe is dt. Okay, now if I get the acceleration at each point on this velocity time graph, and I want to get the AT curve or the AT graph, that's acceleration time graph, I can also plot the acceleration time graph. If I get the acceleration, so let me take my board to the other side. So if I get my acceleration time curve, so if I have something like this and I have something like this, so this is acceleration and this is time. And then my curve goes this way and I take an elemental stripe down here. Elemental stripe down here. So of course, since this is, I didn't put something in this velocity. Look at this stripe. This vertical here is A because the vertical is having A axis. Is having A axis. Okay? Is having A axis. So if I say this A times this dt, so that's going to be dv. So dv, if I cross multiply this, that's what I'm trying to say. If I cross multiply that, dv is going to be equals to A dt. Dv is going to be equals to A dt. Dv is going to be equals to A dt, which is what I can show on this graph. So same thing applies to this acceleration time graph. The vertical here is A, that is this stripe that I took. The vertical is A, and this is dt. that is dt. So if I take my initial time at t1, my final at t2, okay, so I can also plot this acceleration time curve. Now, there's something again I want you to pay attention to, and it is that if you notice this equation that is being, let me go back to the first graphical diagram so that I'm going to show you something. Okay, so look at this first equation here for ST curve. Look at the first, look at the first diagram for the ST curve. So look at this equation here. Look at this equation. If I cross multiply, I'm going to have ds. I'm going to have ds equals to v dt. Okay, so if I integrate my lower limit from S1 to my upper limit of S2, and if I integrate over T, lower limit T1, upper limit T2, all right? If I tidy up the equation on the left-hand side, I'm going to have S2 minus S1 equals to the area under VT curve, the area under the VT curve. The area under the V, you know what I did? I expanded this V dt, so the area. And we have said it previously that if I take the slope, I'm going to get the velocity. I'm going to get the velocity, okay? Now, if I do the same thing for the velocity, if I do the same thing for the velocity time graph, if I integrate my dv, and I also integrate my right-hand side, a dt, and I take my lower limit from V1 to upper limit V2, my lower limit from T1, upper limit of T2. So if I tidy up the equation, I'm going to have V2 minus V1 equals to the area under the area under a AC curve, the area under the AT curve. Okay. Now, lastly, if I lastly, so if I tidy up the equation for the last one, if I have V dv, remember this equation V dv is meant to be A ds, right? Now, so we're going to have our dv squared over 2. All right, of course, the equation is meant to be V dv A ds. But don't forget, we're having acceleration time graph. That's AT graph. This is AC graph. AT graph. Okay. Now, you know that from this equation here, I bring this down. From this equation here, I can then say if I integrate V dv, sorry, not this equation, from this equation, I mean to say V dv equals to integral of A ds. And I have V1, I have V2, I have S1, I have S2. So if I tidy up the equation, if I integrate this left-hand side, it's going to give me half into bracket V2 squared minus V1 squared, all right, equals to the area under AS curve, the area under the AS curve. Okay, so those are the graphical representation of some of the equations that we have derived, the equation under kinematics that we have derived. So it is also possible that we have the, we have AAT curve. It is also possible that we have the AS curve also. It is also possible that we have the AS curve also, which is the equation I've derived. And I've also derived the equation for our AT curve. I'm trying to take my screen back. Where is this icon? Okay. Okay. So we have derived the equation for AT curve. We have derived the equation for AS curve. So let me draw the AS diagram for you. So we have this. So we have something of almost similar to that of AS, but the curve is a little bit different. AS curve. So we have something like this, and we have something like this. So we have the acceleration here. We have ds. We take our position initially at S1, take our position at S2. Okay, so that's that on that. Now, let's solve some questions on this and let's see how it is being applied. And then we explain a few things. So, example one. Example one. Now, consider a particle. Consider a particle. Consider a particle. Consider a particle. Consider a particle moving in a straight line. Moving in a straight line, and assume that and assume that its position is defined by its position is defined by the equation. Okay, so we have x equals to 6t squared minus t to the power of 3, where x is in meter. Okay, so x is in meter and time is in seconds. Okay, so now how do we obtain the velocity, the position time graph, the velocity time graph, and the acceleration time graph? And we'll give it some interpretation. So how do we go about this? Now, the first thing you need to know is that to get the graph, to get the graphical representation, it's not as if you do not need the equation that we have derived. You need them. It is those equations that is going to be leading you to getting the graphical solution. So it's not as if the graphical solution is standing on its own, that you don't need the help of the equation we have derived. No, it is not like that. You still need those equations we have derived. Okay, but just that I want to interpret those equations graphically. So solution now. Solution. So to get my position time graph, the first thing we want to get is, let's get our velocity. So to get the velocity, we are going to differentiate with respect to t. That's x with respect to t. This x is position, so it can be x. So we know that v is ds dt, which is same thing as, if I differentiate 6 to the power of 2, that's going to give me 12, 12t minus 3t squared. That's my velocity. But then, how do I get my graph from this velocity I have here? How do I get my graph from the velocity I have here? Before I move on, I haven't gotten position time curve, right? I haven't gotten that. I've only started solving for velocity. That's a mistake from me. So let me get the position time curve first before I move to the velocity. Your position time curve can be gotten directly from the equation you're being given. All you need to do is to choose an interval to construct your graph. So let me choose, let's say I'm choosing my interval between x equals to, sorry, I mean t equals to, t is the dependent, independent motion. T equals to 0, and let me choose t equals to 1, t equals to 2, t equals to, let me just choose a random interval, so we're going to be fast. Okay. So if that be the case, when t equals to 0, my x equals to 0 also. When t equals to 1, my x equals to 5. Just put 1 into this equation here. 6 to the power of 1 minus 1, that's 5. Then when t equals to 2, my x equals to 16. Just substitute them into the equation. And when t equals to 4, my x equals to 32. Then when t equals to 6, x equals 0. X equals 0. So let's plot the position time graph now. So if I have my vertical as my position, I have my horizontal as my time. So if I have my x in meters, I have my t in second. So let's just give it 0 because of space. 2, 4, 6. And then my time, 2, 4, 6. So if that be the case, let's plot our graph. When t is 0, x is 0. So I'm here at this point in time. I'm here. When t is equals to 1, x equals to 5. So this is t, let's say this is t equals to 1 here. And this is somewhere around 5, and this is somewhere around 1. If I trace them out, so this is my position. So when t equals to 2, x equals to 16. Okay. Let me make this graph so that it's going to contain what we want to do. Let me make this graph 5 on the vertical. Let me make it an interval 5. So let's say 5, then is this small? 15, uh, 15, 20, 20, 20, 25, 30, 35. All right. So let's take it again. So when x is 0, t is 0, the first one is still correct. When t is 1, s is 5. So let's say this is t1, x is 5, something of this sort. So it's here. So when t is 2, x is 16. So 16 is just above this. So 2 is something around here. All right. When t is 4, x is 32. So 32 is somewhere around here. Let me put it here. Sorry about that. Okay. When t is equals to 6, x is equals to 0. So this is t6, x is equals to 0. So if I plot the graph, I'm going to have something of this sort. I'm going to have something like this, goes up, 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 then comes back down. Okay, so that's my position time curve. That's my position time curve. Okay, so how do I get my velocity time curve? So to get my velocity, I have to differentiate my position, right? Yes, I have to differentiate my position. So to differentiate that, we know that V equals to d dx dt. And so I'm going to apply the formula there. So my V, to get my position, to get my velocity time graph. So V is ds dt, and that's equal to 12t minus 3t squared. Again, to get my graph, I have to choose an interval. So just to make it very fast. So when t equals to 0, v equals to 0. So if I put here, if I substitute for t here, 0, 0, v equals to 0. When t equals to 2, because of time, v equals to 12. You put 2 here, 12 times 2, that's 24. Minus 3, 2 squared, that's 12. That's 4. 4 times 3, 12. That's 24 minus 12, that's 12. Then if I put when t equals to 4, then v equals to 0. And then when t equals to 6, then v equals to 36. So if I'm to plot my graph now, if I'm to plot the graph of velocity to time, so this is velocity and this is time. Okay, now let's pick the values one after the other. So let's say this is, we have more of negative 36, not 36, negative 36, negative 36. When t is 6, we have negative 36, not 36. Okay, so that means you have a higher value at the negative side. That's why I have to play my graph. So let's say this is 0. Okay, and I want to give it interval of 2 on the horizontal t-axis. So this is time, and this is in seconds. This is my velocity in meter per second. So if I take an interval of 12, I take this is going to be 12. Of course, you need to be negative towards the bottom side. That will be 24, and that will be 36. 36. Okay, so when t equals to 0, v equals to 0, I'm going to start from here. Then when t equals to 2, v equals to 12, something of this sort, I'm going to be here. And then when t equals to 4, v equals to 0. So I'm going to be here at this point. And then when t equals to 6, v equals to minus 36. If I trace this down, I'm going to be here. So I'm going to have this curve coming down like this. So that's the velocity time curve. Okay, so we move to the acceleration time curve. The acceleration time curve. So again, to get my acceleration time curve, I need to also pick an interval. All right. So, but the first thing I need to do is to differentiate, right? Yes. So if I differentiate my velocity, my acceleration is dv dt. So if I differentiate the velocity, I'm going to have 12 minus 6t. Okay. Again, when you pick the interval, when you say at t equals to 0, a equals to 12, just put 0 here. At t equals to 2, a will be equals to, when you put 2 here, it's going to be 0. At t equals to 4, a will be equals to minus, of course, this is 6 times 4, that's 24, minus 12. Okay, minus 12. And at t equals to 6, we're going to have 12 minus 6 times 6, 36. So we're going to have 12 minus 36, which is going to give us 24. That's negative 24. So if I plot my graph of acceleration against the time, I'm going to have, take this to the right-hand side. I'm going to have this acceleration. So this is acceleration on the vertical, because I have more values to the negative. That's why it's like that. Meter per second squared. Now my time in second. So when t equals to 0, so let's give it an interval. This is 0, this is 2, this is 4, this is 6, and also this is 12. This is negative 12. This is negative 24. which is negative 36. Okay, so if I plot my graph when t equals to 0, a is 12, so it's going to be somewhere up here. When t equals to 2, a is 0, somewhere here. When t equals to 4, a is negative 12, somewhere somewhere here. Yeah. Then so when t equals to 6, a is negative 24, somewhere here. So if I join the graph together, I'm going to get a straight line curve. So that's my AT graph. AT graph. Now, I haven't gotten the graphs. There are a few things you need to know about those graphs. Now, the question initially says that a particle moves along a straight line. All right? A particle moves along a straight line. So something you need to understand is that the curves that we have obtained, they are all known as the motion curves. They are known as the motion curves. However, all right, because they've told us that the particle moves in a straight line, the particle does not move along these curves. All right. The particle does not move along this curve, this STVT. No, the particle does not move along this curve. The particle was, we were told that the particle moved in a straight line. In a straight line. So the derivative of the position of the particle per time gave us the velocity and gave us the ST curve, then give us the acceleration, the VT curve, and then AT curve. Okay, so that's on the graphical representation. So let's take another question to demonstrate this. Let's take another question to demonstrate this. I'm going to write the question now. So this is the question being displayed on the board that we're about to solve. So I'm going to read the question out. The question says, the position of a particle which moves along a straight line is defined by the relation x equals to t to the power of 3 minus 6t squared minus 15t plus 40, where s is expressed in feet and t in seconds. Determine A, the time at which the velocity will be 0, B, the position and distance traveled by the particle at that time. And then we have question C and D, which I'm going to write when I get there. So solution. Now, to solve this question, we can solve it analytically and we can also represent it graphically. So what we want to do is we want to solve this problem and also express it graphically. So the first thing they ask us to find is determine the time at which the velocity will be 0. The time at which the velocity will be 0. So the first thing we want to do now is to get the position, the velocity, and the acceleration, all right, from the basic kinematic equation. So we know that our position x is c to the power of 3 minus 6t squared minus 5t plus 40. So if I want to get my velocity now, so that when I want to get my graphical solution, I'll just come back to this. I'm going to have 3t squared minus 12t minus 15. And then if I want to get my acceleration, which is v dot, same thing as x dot dot, I'm going to have 6t negative 12. Okay, now a part of the question, pay attention, I'm still going to come back to it. I want to scroll up. The A part of the question says the time at which velocity will be 0. So what do we do? The question is being straightforward, right? The time at which the velocity is equals to 0. We have gotten velocity. Let's say this is equation 1. Let's say this is 2. And let's say this is 3. So from equation 2, we have gotten the velocity. And the same, we should get it at time when velocity is equals to 0. So A, the time at velocity equals to 0. So I'm just going to equate my velocity there to 0. And if I do that, I'm going to have 3t squared minus 12t minus 15 equals to 0. Okay, so if I sub that completely, because this is a quadratic equation, I'm going to get solving, I'm going to get that my time, of course, quadratic equation, I'm going to have two values. I'm going to have my time to be -1 second, and I'm going to have my time to be plus 5 seconds. Okay, now, so which of this time are we going to pick? Which of this time is going to be the answer? Our time is going to be plus 5. Our time is going to be plus 5. Oh, don't mind my pen, please. Our time is going to be plus 5 seconds. Okay, so why is that so? That is because it is plus 5 seconds that corresponds to when our motion has started already. All right, -1 does not correspond to when our motion has begun. All right, plus 5 seconds corresponds to when our motion has what? Has begun. So let's plot the graph so that you can see it graphically. That's the essence of graphical solution. Graphical solution makes it a lot more easier. So let's say we have there's our graphical solution. So we have 0. So you know how we do it, right? You pick an interval. Yeah, you're correct. So if I pick, because of time, please, let's say this is 5, and I say I pick an interval here. This is time. This is position, and this is time. Okay. So in this our position equation 1, top here, just want to pick 3 intervals, so we'll be fast. When t equals to 0, x is equals to what? This will be 0, this will be 0, this will be 0, x will be equals to 40. When t is equals to 5, when t when t uh,